Here we have a cylindrical cable of length d, and this cable lays on top of these rails of length L. Okay, so the cable carries a current I, and there's a magnetic field pointing vertically down everywhere in space. So because the current is in a magnetic field, the wire feels a magnetic force, which is equal to I times L cross B. Well, L is the length of the wire, so in this case it's just D. So we have that this is the magnetic force in the wire. And the sine of the angle between the wire's length and the magnetic field is 90 degrees. So the force that the wire feels points to the right, as given by the right-hand rule. And its magnitude is I dB. So the work that this force does is the force times the distance that it pushes the wire, distance of L. And that's equal to the kinetic energy that the wire has right before it rolls off of the rails. So the kinetic energy in this case has two components, because it's moving by rolling. The work, which is equal to the force times the distance, equals the two components of the kinetic energy, the center of mass motion plus rotation around the center of mass. Now, rotation about the center of mass is 1/2 I omega squared, where I is 1/2 mr squared for a cylinder, and omega is v over r. So here we get that the total kinetic energy is equal to this term, 3/4 mv squared. So now we know that the total work equals the total kinetic energy, and all we have to do is solve for v. So we find that v equals this whole thing right here. So now it's just a matter of plugging in what these values are, because we know I, we know the current, we know d, which is the length of the wire, we know b, which is the magnetic field, we know L, which is the length of the rails, and the mass of the wire is that. So we could just multiply this out and we get the value of the velocity, which is that.